All right, everyone. I am here with Rafa Gomez-Bombarelli. Rafa is an assistant professor at MIT in the Department of Material Science and Engineering. Rafa, welcome to the TWiML AI podcast.
Thanks so much, Sam. A pleasure to be here.
It's great to have you on the show, and I'm looking forward to our discussion. We will be digging into a topic that, of course, is near and dear to your heart, but one that you also presented recently at the SigOpt Summit. And that talk in particular was called Designing New Energy Materials with Machine Learning. But before we jump into that topic, I'd love to have you share a little bit about your background and how you came to work at the intersection of ML and materials.
Yeah, thanks very much. So I was trained a chemist. I did my undergrad studies back in my home country in Spain, and I started working and doing research in the lab. I broke all the glassware, and it was decided that I had to be a theorist because I just couldn't be in a lab. I did simulations, so I was using the laws of physics and a technique called density functional theory. To simulate what a material would do before you have to make it. And after that, I came over to the States. I was at Harvard for a couple of years working with Alana Spuru-Gutzik, learning how to do, 100,000 simulations instead of one, right? So bootstrapping our own big data. And at that point, we realized, this was 2015, and we realized that we didn't have physics problems anymore. We just had data problems. Right? We had this oracle that could tell us whether a material was good or not, and we just had to navigate these high dimensional design spaces, right? And since then, after a brief stint in industry and coming to MIT, this has been what we try to do, right? How do we interface this ability to predict with physics, right? Very rigorous, can extrapolate, just expensive, and the ability of machine learning to you be used as a surrogate for the physics or as a way to invent new materials. And that's what I've been doing for the last few years.
You mentioned density functional theory. What's that all about?
It's a simulation technique based on quantum mechanics. So it's very popular. It's as accurate as some of the most expensive simulation techniques, but tractable. So it scales for the computational complexity people out there. It goes with n cube, so the size of your problem, the cost you pay is the cube of the size of your problem. When we get to quantum computers, it will be obsolete, but in the meantime, it's kind of the best trade-off between accuracy and speed. And by the way, there was this beautiful DeepMind paper in applying machine learning to the operation of DFT just a few weeks back on Science. So it's definitely another exciting place for the community to be interfacing machine learning and physics.
You mentioned that DFT scales with the cube of the size of the problem. What characterizes the size of the problem? Or more broadly, how do you formulate the types of problems that you're trying to solve for simulation and for DFT?
The size of the problem is actually the number of basis functions one uses to represent electrons. But at the end of the day, it's the number of electrons in your system, right? And the number of electrons in your systems is how many atoms. So we're an atom crowd. We track the nature of our problem atom by atom. So meaning that typically we're limited to asking questions of systems with tens to hundreds of atoms.
And maybe let's take a step back and have you take us deeper into the specific problems that you're trying to solve. Ultimately, you're trying to design new materials. Is that right?
Exactly. And there is fundamentally two ways in which we think about designing new materials. One is what we call virtual screening, which is enumerating a long list of anything that could potentially work based on intuition, or maybe things we extract from patents, or maybe we knock on our collaborators' door and ask them to draw some molecules for us, and we end up with a list, a closed space of candidates we want to evaluate, right? And in this case, we can evaluate them with experiments, or we can evaluate them with simulations. Experiments are extremely expensive. Simulations are less expensive. And the name of the game is how do we build these proxy functions that are as good as these oracles, as these simulation or as these experiments, but are much cheaper, right? And as robust as possible, so we can apply them over all our design space consistently and in a trustworthy fashion, right? And then we set up active learning loops where we go hunt for the data that the model really needs based on uncertainty, so we can quantify the uncertainty that this model has on its own predictions, and find those points that the model is not very certain about, maybe good, maybe bad. It doesn't really know, so we go add them to the pool and set up these active learning loops to screen over these finite spaces. And then the other way to think about design, which is sort of flipping the problem, right? Rather than being given a list and having to walk one by one over every member of that list, seeing if it's good or bad for the property we want, is using inverse design techniques, where we flip this function. And instead of having a function that goes from structure to property, which is the way one typically thinks about materials, we try to make the reverse function, a function that goes from the property you want to any structure, any material that could realize that. And this connects with machine learning techniques such as generative models that do precisely that, right? They invent new members of a distribution. People do this with celebrity faces or text, and we do it with crystals and molecules.
Got it. To be clear, machine learning plays a role in both of these directions. In the virtual screening, you're using machine learning to essentially you take the place of experiments to create a proxy or a set of proxy functions that you can apply to the candidate materials instead of actually putting them through an experimental process to validate them. And in the inverse design, it's trying to predict the materials that will ultimately deliver these properties you want.
Exactly. So it's two sides of the same coin, but of course what the models need to do is very different. And there is a unique set of challenges in each way, because predicting properties from a structure, so screening, is an older task, is a more established way of thinking. The tools there are fairly established, and people have spent quite a bit of time in the last few years thinking about representation learning for materials, right? This is the key here. Text has its own representations, and machine learning models have been made that are really good for reading text. Images are their own representation, and very good architectures have been made for images, for pixels. And then the nature of the materials we're looking at is atoms, right? This goes back to what is the ultimate bit of information in our system, and it's atoms, and it's how they're connected to one another. So there's been a lot of work in making architectures for atoms and molecules and materials, and graph neural networks are the key winners. So the chemistry and the materials community have been big contributors to the fundamental algorithm development in graph neural networks, because it's the workhorse that we need to read matter, right? It's our representation to read matter, and it has all the right invariances that we need to put matter into an algorithm. But for writing, it's very different, right? Writing matter turns out to be really hard, and there is still open questions about what is the best architecture to write graphs, right? It's okay to write sequences, but it's not as easy. There's a number of invariances that are hard to control for in writing matter. So we're very excited about that second part.
Given these two approaches, is your work focused on inverse design, or is it shifting to inverse design? Do you see virtual screening as kind of this historical, workhorse of the field, but it's dated, or will they coexist? And you actively working on both?
In terms of screening, so for instance, we just had a very exciting paper where we went back to a class of materials are called zeolites. They're nanoporous materials, yeah, zeolites. It's actually your cat litter. This is what that's called, the sand that you use for your cat. That's a natural class of zeolites, right? It's a material that's out there that people can extract from the earth, and we can also make synthetic ones that are more sophisticated. But they're all in the same class of nanoporous materials that have these small pores that fit the thing you want. And they're using catalysis, they're using oil and gas, for instance, and they're using biomass conversion and sustainable catalysis. And we've moved the needle in that field by doing a lot of screening. So we've set up our forward functions and just executed hundreds of thousands and millions of simulations at a scale that was, enabled by new technology. But it was a very much forward problem, right? So a place where we just went through a long list. and we were able to invent a new material that seems really good for car exhaust, for cleaning up the fumes coming out of cars or from
I thought you said
industries.
cat exhaust for a second.
No, that's good. No, this is for diesel. So diesel engines need some treatment on the flue gas that this material could be very good for.
Okay.
So that was state of the art, but going through a long list. But of course now we're okay. What else is out there? So typically in our experience, before we can formulate the inverse problem, we typically will need to have formulated the forward problems. Like, well, if it's unlikely we're going to be able to invent out of the box before we've mastered what's inside the box. So we see them more as a sequence, as a 1-2 of exploring what's the bounded universe that people can think of, and then going to sort of the unbounded universe of what people hadn't thought of yet.
And so it's less because the techniques that you apply in the inverse design phase rely on specific artifacts that you created in the forward phase, but rather more about just the understanding that you've developed in going through that forward phase? Or is it both?
I think it's a little bit of both, because just the data for the inverse model will need to have come from a forward model, or from the same data that enable a forward model. But also the architectures, like I said, the architectures for forward problems are very well developed. In this field, graph neural networks are really accepted as a good surrogate for almost anything you could simulate. You could train a graph neural network to replicate, and that will be trustworthy and consistent. But inventing new matter, dreaming up new matter, it's actually hard. There is a lot of subtleties that we haven't really been able to embed into algorithms in a trustworthy fashion yet. And we had recent work, for instance, with peptides in the therapeutic space, inventing new peptides to help deliver new drugs into the cell, to the place where they need to go. And this was a place, where inverse design has worked nicely, because it's not too hard of a space to take steps on, right? So imagine inventing a new face, right? Requires an algorithm to figure out that you need to have 2 eyes that need to be at the same height, and a nose and 2 ears. So there's a bunch of underlying rules about how to invent in each space, and the small molecule space where many of new drugs are has turned out to be really, really hard. And computer scientists, there is sessions at every computer science machine learning conference now about how do we invent new drugs with machine learning, because it turned out it was harder than we originally thought.
You mentioned that in the inverse design problem, there are invariances that make that difficult. Can you elaborate on those invariances?
I'm going to plug here my good colleague Ted Schmidt, who started here this year at MIT, who is the real expert about how to handle symmetry and equivariant neural networks, which has been a key part of representation learning, like I said, going into the forward models. As I said, materials are, at the end of the day, 3D arrangements of atoms. So we typically will be asking of the model to write a 3D arrangement, a 3D points cloud, which is by necessity translationally and rotationally invariant. That's not too hard, but it's also permutationally invariant. It doesn't matter which atom you call 1 and which atom you call 27, right? Nature doesn't have little tags attached to each atom saying that they're 1 or 2. But most machine learning algorithms that write sequences, anything you write as a sequence will have some canonical ordering, right? There is some order your readout algorithm is going to give. And it turns out, right, that then we need to somehow figure out how to take into account this permutation invariance over atom indexing. And it has been hard. There is no immediate answer. The easy answer is to do data augmentation and just throw in the n factorial permutations into your training data, and then your model will be brute forced to learn how to do permutation invariance just by example. But of course, that's, it's factorially bad. So there is, architectures and maybe growing graphs out of graph coarse graining, right, where you constrain, you keep a little bit of information such that the connectivities between these coarse-grained particles span a basis to grow the rest of the architecture or of the molecular structure. So there is a number of sort of up-and-coming solutions, but there is no immediate way to deal with a permutation invariance on the generative models.
To what degree are the generative models also graphical models, or are they? Do you lose the benefit of graphs when you're working in the generative domain?
Exactly. Yeah. This is so in principle, this is a place where materials and molecules diverge slightly. Typically, in materials, it's not immediately obvious what the graph is, who's connected to whom. It's a little bit more arbitrary when people, when you're looking at a steel, there is no clear chemical bonds in a way that it immediately can be interpreted as a graph. So it's a little bit more on the point cloud. And there was this beautiful paper just a few weeks ago from Tian Xie, who's just moving to Microsoft. If it's anybody out there that knows Tian, he's a shout out, where he is creating 3D materials through gradient fields. So he's moving around the atoms and finding the places where they work best in 3 dimensions. And the molecules are typically seen as graphs. So typically, where solid materials are not graph or not seen as graphs, molecules are typically seen as graphs, meaning that you have, the chemist, when a chemist goes to the whiteboard, I don't know if I have any molecules on my whiteboard, but when a chemist goes to a whiteboard, they can draw a molecule as a graph. In any case, writing out graphs turns out to be really hard anyway, because they have the same problem. There is still a permutation invariant, but the architectures that write graphs need to deal with this invariance somehow. So either molecules and materials and solids are slightly different in terms of how graph or 3D they are, but at the end of the day, they both suffer from this complexity of permutation invariance. So it's a general problem.
In creating the generative models for inverse design, are you using the same types of models that you'd use for celebrity faces, StyleGAN, that kind of thing? Is it just that the training data is different, or are there tweaks to the models and architecture that you use for this particular problem? How dramatically different are they from, what you might use in other generative domains?
So the first generation of generative models from a few years back, they mostly co-opted text-based generative models for the reason that there is this hacky way to represent molecules as a string. So there is a notation that has been used since the late 80s where a molecule can be written as a text string. Again, it's a permutationally complex problem because there is, n factorial ways to order the atoms. So it hasn't solved the permutation invariance at all. But it's very easy to move over to text-based tools. So, back in I think 2016, we used variational autoencoders based on inspired by a Bowman paper on continuous generating sequences from a continuous space. And folks have made next character predictions, so making a molecule as a text string, writing one letter at a time. Just the model looks back at what it's written so far and keeps going. And then the natural next step was to apply transformers to this representation. So we've co-opted text-based models for generation, but we've been operating on a imperfect representation. This string is not what a molecule is. So we've hacked the representation in order to leverage NLP. And then there's been some progress on using a more native representation at write-out. But like we say, we deal with the challenge of writing graphs. And there are examples, for instance, there is rationale or building block-based models. For instance, the language of chemistry typically involves substructures that are discrete and well understood, and they're always the same. And the analogy could be writing text letter by letter or word by word, right? So there is if you're going to write a molecule, you could write it atom by atom, or you could write a functional group by functional group. And that's how chemists have thought of them for a long time. So it has made sense for folks to make these hierarchical models that rather than trying to write every atom, every individual atom in the molecule, have the ability to write whole sets of atoms collectively as, I want to draw a benzene ring right now, rather than to draw explicitly the 10 atoms that make a benzene ring. So it's combinatorically better, right? Because you don't need to compound all these right choices in a probabilistic manner.
And so you've mentioned the various ways to co-opt the text-based generative models. Have there been any efforts to do the same with the more visual generative models?
Not for writing molecules. So really there hasn't been an obvious connection. Typically, the resolution of pictures people are interested in are 100 by 100 pixels, right? There is tens of thousands, hundreds of thousands of decisions to be made on a pixel by pixel basis, and maybe you use a GAN for hyper resolution compared with a VAE for the underlying, or a flow model that they're a little bit blurrier. But at the end of the day, we need to write, I said tens to hundreds, right? We're going to have to write hundreds of tokens for a molecule. So really the tools that operate for images haven't really been applied to writing molecules. There is this interesting problem that has come up in the last few, I would say, months, which is how do we use machine vision to read in handwritten molecules, right? So if when a professor goes and on the whiteboard, or some chemist was writing in their lab notebook in 10 years ago, this compound is really helpful for headaches, right? And that's in a paper notebook somewhere. How did you set up a algorithm that will look at that page, at that handwritten molecule, and transform it into a computer readable representation, like these strings I was talking about, or a graph or something? And that's a place where the machine learning and the machine vision tools have been applied, are just being applied these days in chemistry, which is read handwritten molecules from folks' notebooks. So that's a state-of-the-art place where segmentation and all these tools are being taken over to chemistry.
And someone's collected a data set of handwritten lab notebooks?
Yeah,
Oh.
exactly. I think there was this Kaggle not that long ago set up by a chemical company, if I recall correctly, precisely for this, right? They've realized they have all this data in their notebooks, so they've labeled a fraction, and they've asked the community to make the algorithms to go, label everything else. But yeah, it's one of those instances where it's worth to bite the bullet and just annotate your own training data. And this is the one problem we don't have with our physics, is that we always have this oracle to go to, right? And this is the part where bootstrapping our own data has been so satisfying in the type of research we do, is that we don't need to go to this mechanical Turk to get annotations, right? With simulations, we know, what it's a finite cost. We know how much effort it takes to get new data, and it doesn't involve any operator time to get more data.
You mentioned that with regards to the simulation and data augmentation, that that's one way to get around the permutation invariance, but then you have this kind of factorial effect. Is that the factorial effect on the compute time on the simulator, or does it show up elsewhere?
So that would show up in the number of rearranged versions of the same data you need to show to the algorithm, right? In order to be confident that an algorithm has learned that it doesn't matter which order the atoms are at, right? If you need to teach, that 1 to 16, it doesn't matter what the order is. In principle, in order to be certain, you will need to show the model the 16 factorial combinations, right? So you would take your own training data and rearrange it such that the same molecule is represented by a different indexing. And again, people do this in machine vision all the time with the invariances that their model should hold, right? That's what folks, rotate, zoom, add a little bit of noise. So this type of approaches, the analogy in chemistry would be to rearrange the order of the atoms such that the model learns to be invariant.
When you're doing the simulation, are these kind of hand-coded simulations that you're building typically, or are you using simulation packages or tools?
Yeah, when we go and do 100,000 simulations or of some process, we typically rely on these very well established codes and these very well established algorithms for a number of reasons. One is that, just like Facebook, 1% incidence is still tens of millions of problems. We need a lot of nines in the percent success of what we do, right? We need 99.9% success or something of that scale. So we need these very robust codes and these very robust algorithms that are time tested. And the second question is also around the social aspects of credibility. If we're going to invest and choose one level of theory, one simulation package, one choice to build machine learning on top, right? We're going to make, for instance, right, we made a data set using that produce 30 million unique molecular structures. And we put it out there for folks to have a gold standard for molecular structure. It needs to be something folks will accept. If it's something we just concocted at home and then we go out there and try to convince folks that it was really the best possible physics we could have, there is a social aspect to in making sure that we're using time-tested, well-accepted underlying ground truths to then build the machine learning upon.
I'd like to go a little bit deeper in terms of the relationship between the simulation and the modeling. Can you talk about how the simulation results drive the modeling effort?
Yes, there is this long line that goes from all physics and no data science to all data science or all machine learning and no physics. And this is what we try to exploit or find good opportunities to make a difference. So, for instance, there is a simulation technique that's called coarse graining, which consists of instead of simulating your system at full resolution and keeping track of where every atom is, you decide that some atoms are going to move collectively. It doesn't really matter how they vibrate and oscillate with respect to one another, and you just need to track them collectively, right? So it's a very effective simulation technique. It allows you to be faster for a number of reasons, right? There is fewer particles to track, but also when you propagate your system forward in time, you can integrate for longer time steps. So you can only take snapshots of your system at longer times because there aren't really any fast motions anymore because they were suppressed by coalescing these particles into bits. So that's a place where we found machine learning was really helpful because there is a number of decisions to be made. There is two decisions to be made in coarse graining. The first one is which atoms should go be in the same bit, right? And sometimes it's obvious, but sometimes it's not immediately clear what the best low-dimensional representation is. And then machine learning has been great at learning low-dimensional representation. So this is a problem where we use autoencoders to take all atom systems and learn reduced dimensionality representations that then we do physics on, right? So we learn what the laws of physics are that drive the evolution of the coarse-grained system, right? And the coarse-grained system will still evolve under what's called Hamiltonian dynamics. So we need to learn what the energy is, what the relationship is between the velocities and the energies of these coarse-grained particles. And that, again, that's a supervised task where we make the coarse-grained system reproduce the behavior of the all-atom system, right? So this is a place where we replace two hard problems, deciding what to compress into which bits and what is the interaction potential in the coarse-grained representation, both of which are sort of painful and not easily solved by classical techniques, using an autoencoder, using a data-driven approach that learn both the optimal compression and also the optimal interaction potential. And just in these last few weeks, we've also made the last step of the tool, which is generative, which is to go get full resolution out of the coarse-grained system, right? So there is some information that we threw away when we compress our system into the coarse-grained representation, and then we can use a fully generative approach based on an equivariant strategy to up resolve, right? Like folks do with images, and when they do a super resolution, this would be an analogous chemical super resolution, where we start with these beads that ate up the full resolved atoms, and stochastically and following the right statistics, recover the full atom representation of the system, right? And this will allow us to simulate proteins faster. Not just, AlphaFold has rather solved the static structure of proteins, right? But the training data and the task that AlphaFold solves is the structure of proteins at cryogenic temperatures, not the fluctuating temperature-dependent behavior of proteins at real temperatures. So this is a type of technique that would allow one to simulate the dynamics of proteins at much lower computational cost.
I think what I'm hearing is that there's across your work, there's this dynamic relationship between how simulation is used and how machine learning is used. And when you talk about simulation, you're typically talking about it in the context of like it is informing the physics understanding. Like it is the thing that you're using to understand how the molecules are behaving in either this kind of forward or reverse approach. And I think part of what drove the last question, and maybe I'll ask it more directly, is are there any ways in which you're using simulation that is more like what you might think of in reinforcement learning, where the simulation is the training or is part of the training of the model?
So I agree definitely with your first point, right? The way we're thinking about, I think we think about physics, as the it gives us these really trustworthy rules, right? We need zero data. Once we have a law, there is we it will hold up. It's universal, right? We get some universality that is really appealing, because it means that we can be a lot more scarce and sparse on the data side, because we know, there's some underlying structure in the form of laws that we know how to follow. I'm trying to think examples of reinforcement learning. So folks have used reinforcement learning to write molecules. I think the most compelling examples are to do reinforcement learning over what you would do in the lab. So the operations now, rather than writing the molecule as a assembly of atoms, and who knows, how one would go put these atoms together in the lab, is to use reinforcement learning over the chemical operations that you would do in a lab, like get this precursor, put them together at this temperature, and we'll make this other intermediate, and I will put together with that precursor. And this is a place where, the trees are wide. There are very many options, right? There's millions of molecules, so there's millions of precursors you could use at any time. So it's a very wide tree, but it's not very deep. There is only, if a synthesis requires more than 6 or 7 steps, it's probably not very good. So it's slightly different from the way folks typically apply reinforcement learning, where they have sort of these really deep decision problems. But the number of options at any given time are not that broad. So there is some subtlety about how to transfer those tools. But in writing molecules, there is some, inventing new molecules and how to make them at the same time. There's been some exciting developments in applying reinforcement learning, thus simulating in the machine learning meaning what this molecule would do as you build it up.
One of the topics that you covered at the SigOpt Summit is the way you incorporated hyperparameter optimization and optimization broadly in this process. Can you speak a little bit to that?
Yeah, this is something that I think has happened in every project, and has happened again since the summit, where there is there's some task, some way we're trying to think about the interplay of physics and machine learning, where we want to invent something, right? We want to make a model that samples from the Boltzmann distribution. Instead of having to do Metropolis, Hastings, Monte Carlo, we just want to have draw good draws all the time, rather than drawing lots of bad draws. So we train a machine learning model, and the first few weeks the student things are not quite working, the gradients are not flowing back, but at some point the first model is trained. We run it, and it sucks. It doesn't do a good job. It works, but it doesn't work well. And every student is like, oh my, Rafa, like I wasted all this time. Like, no, now you go do hyperparameter optimization and just plug it in, and you will get the set of, define the widths, the heights, the stopping. Well, there is all these choices that are out there that we don't want to have to worry about. And 9 out of 10 times, after a few tens of calls to the SigOpt interface and tens of experiments, it turns out things work. And this has happened many times where.
Do you think is that the way that folks historically think about HPO? Like I think that, often folks think about it from the perspective of it's kind of the icing on the cake. Like you need something that works pretty well and it'll get you an incremental little boost. But what I'm hearing you say is that it takes something that kind of sort of works and actually makes it solid. Like it helps you bake the cake as opposed to the icing, to top off that analogy.
Yes, exactly. And it might have to do with the fact that these are sort of new tasks, right? They're niche tasks that, we're inventing the task and the architecture at the same time, right? There hasn't been a competition for the last 10 years for folks trying to make the best Boltzmann sampler of atomic configurations, right? So then we're sort of trying to define the nature of the task and how to score how good we are at it, and the architecture that does it at the same time. Plus, most of the tasks we're thinking about have some history on the physics side, right? So then the baselines, there are, this pretty easy baseline, which is just do what everybody has done for a long time. Meaning that, we take our first stab and typically we're below the traditional physics-based approach. Like, we try to do our machine learning version, and it's worse than what people's intuition have accumulated to over the last decades. Right? And then the thing that gets us over the line is HPO. So in our case, I understand where you're coming from, but in our case, it's typically more of a discrete change. This is worse than what people were doing before, to then be better than what people were doing before, by combining not just the architecture but the right choice of decisions in the hyperparameter.
I'm maybe inferring a bit, or maybe I should ask. I would think in the domain that you're working in, it doesn't necessarily help you to get some unicorn combination of hyperparameters that works on a very specific set of data. Can you talk about the relationship between HPO and the stability of the models that you're looking to produce and able to produce?
This is the Achilles heel of a lot of the machine learning applications to chemistry, is that chemical space has turned out to be notoriously hard to interpolate on. It has proven again and again that both for the nature, molecules are tricky beasts, and there are cliffs in small changes in chemical structure will result in large changes in property, just because that's the nature of the problem, and that's fine. But there is also something that has proven to be really hard to learn, right? These typically machine learning models over chemistry and over materials really struggle with domain transfer, really struggle to transfer to other related tasks. For instance, pre-training over language models, it's everything needs to be pre-trained. Even pre-training on a different language helps. Like you train a model on English and it will do better at French. And that's not intuitive, right? And we have found that is not the case in chemistry. We found that it's typically, you train on toxicity and then you try to predict, solubility. And there is no connection between the two tasks at all, or very, very, very little. Sometimes it's counterproductive. It's one of those things that has proven really hard. So in terms of hyperparameter optimization helps when combined with setting up the right test architecture, right? So you should be testing on far away, well-defined, different buckets of chemistry, because it's very easy to trick yourself into overestimating the performance of your model. When you show it related chemistry in train and test, you get overconfident, and then when you go try on actual different molecules that you haven't thought of yet, things break down. So this is a place where the combination of the right train test strategies and hyperparameter optimization can help. But on the representation learning side, there's still work to do in making these transferable machine learning models over math.
Can you elaborate a bit more on the train and the test and the distance between these chemistry regimes, and maybe give a concrete example from your experience?
Typically the first instinct is to do, given a bunch of data, is to do random splits, right? You train on 80%, validate your choice of hyperparameter on another 10%, and keep 10% on the bank until the very end, just to make sure that evaluate the performance in a realistic, unseen data set. And this typically works reasonably well in many tasks. But over chemistry, we have found that models will transfer well to chemistries that are really nearby to the training set. So for instance, we just had a paper out where we compared the color of a molecule in a solvent, right? So I put this molecule in water, it's red. I put it in alcohol, it's blue. I put it in toluene, it's going to be green. So if we split randomly, the combinations randomly, we might end up with the same molecule in train and test, just in different solvents. And we do amazing, right? If we've seen the molecule in water, we're going to be amazing at saying what it does in toluene. Then we can split in terms of the chemistry, right? So if the molecule is in train, it cannot be in test regardless of the solvent, right? And we do still fine because we're letting similar molecules leak between train and test. But then if we do what's called scaffold splitting, which means if these molecules belong into the same general group, if they share a lot of attributes, then they need to be together in train or together in test, right? This scaffold splitting is of the highest tier split for molecules. Then things suddenly break down and get really hard. So in terms of performance, I would say we were less than one color in the rainbow away, right? Like if you think about the accuracy of color, you can think, the qualitative is like one hop over the rainbow. We were better than that, right? So if we said yellow, it was yellow, maybe it was orange, but it wasn't definitely blue. And once you go to scaffold splits and you really force the model to learn how to do new unseen classes of chemistry, then we're talking maybe two colors on the rainbow. I think things get really hard. And this was our experience with color, but it's the same with toxicity, with potency, with all the properties that folks care in medicinal chemistry. And it's just hard to quantify how your model will do when you show it new chemistry. But of course, we want the models to invent new chemistry, right? We don't want just to decorate molecules we knew already. We want them to tell us something new and exciting. And that continues to be a challenge for the community.
And so, to what degree does this broadly change the way you think about generalizability in your domain?
A lot. It's this ongoing discussion. What do we do? For instance, there is another class of models we use. They call interatomic potentials. They try to replicate the expensive DFT, right? So if I move a molecule, what's the energy price of distorting, stretching, vibrating the molecule? So DFT is good at that, but it's just too expensive. And I want to simulate molecules for a long, long time. So we can achieve, outstanding performance for a given molecule in its own distortions. We can achieve outstanding performance. There is the error of experiments. When people compare theory to experiments, the uncertainty of the experiments is higher than our ability to replicate the theory, right? So we nail down the theory with machine learning to the point that we just don't know if the experiments agree or not, because experiments are noisier than our ability to replicate theory, right? This is what they call chemical accuracy. So machine learning models are indistinguishable from theory for a single molecule. But now you try to mix in multiple molecules at the same time, and the error goes up. So it's really hard to, again, what's called this conformational space. So just moving pieces of the same molecule. It's amazing. We do 0.1 kilocalories per mole. That's the units we use, kilocalories per mole. We do less than one. One is chemical accuracy. Less than one is your machine learning is as good as your underlying theory that you're trying to replicate. Now you try to mix in new chemistries, and suddenly things shoot up, especially if they're unseen chemistries and unseen families of molecules. They get 10 times worse. They get 25, 50 times worse. So it's hard, because it's hard to quantify similarity too. We don't really have, and then there is people like Heather Kulik here at MIT who has done work in quantifying how does my machine learning model see similarity between these two molecules in a way that I can use it. But it's a very much open question. I don't have a good answer about how to make transferable models over chemistry.
That last work you described makes me think of some kind of molecular embedding space, and I've got to imagine that's been a lot of thoughts been put into that. Is that working yet?
Yep, you're spot on. So the graph neural networks create a vectorial embedding for molecules, and they do a great job at that. And then you can take, your distance, maybe Cartesian, maybe you do a cosine distance over this embedding, and that correlates relatively well with the error in the model. Can we do better than that?
But there's a but there. You were saying that the similarity is very difficult in this space, and I'm imagining this goes back to these cliffs that we're talking about, like the distance measures are they like nonlinear or something like that, and they just fall off a cliff?
Exactly. So there's two things. One is this very non-linear nature of the manifold, right? There's this very non-linear nature of the response surface, meaning that you're gonna get surprises. This tiny tweak over structure turns out to be a tremendous tweak over property, and the embeddings may struggle to capture that. And then the second part is that this is all property specific. So we've made a distance for this property. But because there aren't really large data sets with all the properties at the same time that cover all of chemical space, we have the same problem again of transferability, right? Okay, we've managed to make one distance that really works and correlates with error in this task. But again, the distance and the embedding similarity for toxicity is going to be very different from the embedding similarity for solubility. So we're back to the lack of transferability across tasks. So even if you've gotten transferability across chemical space to some degree, you're still struggling with chemical transferability across tasks.
Mm-hmm. Got it. It's not similarity of two molecules in some absolute physical context. It's relative to some property that um, you built your whole space around, your whole representation around, and those are non-overlapping or non-sufficiently overlapping when you want to look at broad sets of properties.
Indeed, and we go back to the pre-training, because one could try, well, we could pre-train in an unsupervised way, with graphs. People do, you delete some nodes and you ask the model to put them back, right? This graph completion pre-training, or in language there is analogous strategies, but they don't really help with chemistry. So the embeddings that you learn from doing unsupervised completion type of tasks are not really helpful for downstream supervised tasks. Or, there might be 1% for this and that, but it hasn't dominated and solved our challenges in the same way as it has in other domains. So yeah, you're spot on.
One thing we haven't really talked about is you've talked about this forward problem, reverse problem, and how in the inverse design problem you are starting from these desired properties of the material and trying to come up with the materials. And we haven't talked about kind of the feasibility or realizability constraints beyond the desired properties. Is that something that do you have the luxury of, hey, we're in academia, we don't have to think about that at all?
No, I mean, no, definitely not. Definitely not, to the point that there is a broad spectrum of answers there. So some folks have found out that it's so hard to get things made that what they should be doing now is robots to make molecules, and there is a big push in the community to, okay, let's go to the next step and computerize the creation of molecules in the lab, right? So let's make robots that pick this up and mix it up and whatnot. And here I need to plug my colleague, Connor Coley. He's among others, one of the folks that's leading the charge in making machine learning models that write how you should make the molecules. This is the reinforcement learning over steps in the lab that I was describing, right? That's the idea, right? So you not only your steps, your actions for the machine learning generative model mimic the actions you should take in the lab, right? So if something can be written by the model, it can be made in the lab. So that's another strategy. For materials, it's a little bit better because materials are typically made at high temperatures and with this sort of, you've seen casting, right? Like you melt iron and you hit it with a hammer. So typically we're more driven by thermodynamics mostly. So typically, just saying that if this is the most stable combination of these elements I could make, that's typically how you decide if a material can be made, right? If this is where tantalum, niobium, and wolf and tungsten want to be, and this is the lowest energy they could have, then I know I can put them in a chrysol, I can melt it, and I get the right alloy. So
but one thing I remember from that materials class is all these hysteresis effects where the actual the properties are nonlinear with heat and temperature and how things are made.
Yes, that's kinetics, right? So exactly, that's the typically. So for instance, right, you would need to heat more than you ideally would have, right, to make sure that your system really melts and then you can slowly cool it. So there are nuances in terms of the execution on how to make them in terms of which process parameters. And then there is Elsa Oliveri here at MIT who does natural language processing over chemical recipes for materials. So she's got this robot that reads papers and tells you, you know what, you should sinter this at 1,000 degrees, or you should sinter it at 1,200 degrees, depending on the pore size you want, right? So there is folks that are thinking about that, but typically the binary decision of this is makeable, this is not makeable in materials, it's energy. And we can get energy from physics, and we can get surrogates for energy with machine learning. So we're typically fairly confident whether we have support or not in terms of is this just accessible or not. And again, this is a place where molecules are harder or less tractable because energy, if we were talking about energy, everything would be CO2, right? Like if it was just energy, oxygen would oxidize everything, and our whole world will be carbon dioxide and water. So there's a lot more nuance about metastability and energy helps. There are energetic arguments to be made, but there is a lot of execution practicality arguments that are based on the way we make molecules today, and that's the challenge, right? That molecules that wouldn't seem makeable 20 years ago are standard now, right? So how do you embed that into a machine learning model, right? The rules of what's makeable are very practical, right? They're based on the technologies available to us at a given time.
And is that, well, maybe I'm asking you back the question that you just asked. How do you pull that into a machine learning model? And in particular, are those constraints that you bake into the model itself, or are they things that you can work with at the HPO level, where the SigOpt in this case is keeping those constraints in mind as it's trying to find trying to navigate the hyperparameter space for you?
I don't think we have a good answer for that. So in the past we've added this sort of chemical beauty or chemical complexity descriptors, and then made them part of our objective function, right? So we want something that makes accurate, performing, and accessible molecules, and we've tried to navigate the Pareto line of getting the best possible combination of all these things at the same time. So that's one way to think about it. And the other way is to make the algorithm itself, the architecture that you're using, mimic what's makeable in the lab, and the steps and the operations that you take are what's makeable in the lab. But of course, like you just said, that's less than what's makeable in general, because there might be this one step that no one has made in the lab yet. At the moment, somebody makes this new catalyst or this new coupling, and the paper gets out, then there's going to be this new way of making it. So there's no open answer these days And I think folks are taking sort of any and all approaches at the same time.
Awesome. Awesome. Well, Rafa, thanks so much for taking the time to share a bit about what you're working on. Very cool stuff. And I really enjoyed chatting about it.
Thanks so much, Sam. It was my pleasure.